much. Thanks for the invitation to speak at this Cyclic Homology birthday conference. So my talk, the theme of my talk is the question of whether some homology theory with analogous properties to those of HP, periodic cyclic homology, can be defined over characteristic P. Okay, so I will start, if this works. Yeah, I will start by looking at the properties that HP has in. I'm talking always about a purely algebraic situation. Then I will consider something more with a more analytic flavor, but say I have algebras over the field, and the field has characteristic 0. And so, well, to any algebra, one associates its periodic cyclic homology. And this theory has several desirable properties. First of all, it is symmetry graded. Second, it is homotopy invariant. And here by homotopy invariant, I mean in the polynomial sense. So in particular, HP of an algebra and HP of the polynomials with coefficients in the algebra are one and the same, and the isomorphism is induced by the inclusion. This was proved by Thomas Wood-Willie in a paper in the old topology journal, 1985. It is also matricially stable, by which I mean that the inclusion of an algebra into M infinity, the finite matrices with coefficients in the algebra of arbitrary finite size, the inclusion in the upper left-hand corner induces an isomorphism in HP. From this, you can derive Morita invariance for unital algebras in the usual sense of Morita invariance. And using excision, which is another of the properties that I will mention HP has, you can go further and prove, more general excision, more general Morita invariance results. So, for example, Joachim Kunz has some paper about this. HP is also nil invariant, by which I mean that it is invariant under nilpotent extensions. And this is also in Wood-Willie's paper that I pointed out before. And, well, the big theorem that took longer to prove by Kunz and Quillen says that HP satisfies excision. So that means that to a short exact sequence of algebras, there corresponds a long exact sequence of periodic cyclic homology. Not so long, because since it is two periodic, it's a 6-term exact sequence, round sequence. Okay. Yeah, and that's the reference. And well, so moreover, apart from these nice properties that, for example, except for the C mod 2 C graded part, homotopy algebraic K theory has all those properties. There are other theories that have these properties, and if you allow, if you are in a C-star algebra situation, say, or Banach algebra situation, then your Banach algebra K theory is also similar to C graded. So there you have other examples. But what distinguishes HP from these other theories is, well, a certain linearity, which can be described as saying that the HP is the non-commutative version of the RAM. So, and in the commutative case, it recovers the RAM. And by the RAM, well, one has to say what the RAM homology means, what the RAM homology theory is. And well, this is the subject of my next slide. So as so many things that are right in algebraic geometry, in foundations of algebraic geometry, this one is due to Grothendieck. This is what he introduced as infinitesimal homology. It's in this exposé sur la homologie des schémas. So how is this defined? So say this is more generally defined for schemes, but say we have a commutative algebra, or if you will, an affine scheme. So I have a commutative algebra over my field K of characteristic 0, and I want to define H-inf. Okay. So here's a procedure or recipe. You first write A as a quotient of a smooth algebra. So say your algebras are of finite type. So then you may write A, because it is of finite type, as a quotient of a polynomial ring, and which is smooth. So that's your representation. What you do? Well, you take, so here I put a long series of identities. Let me start by the last one. So what I wrote at the end of the line, of the second line, was the RAM homology of S hat sub I. So that means the completion of S in the I-adic topology, which is the homology of the completed, the adically completed complex of commutative differential forms on S. Or what is the same, the inverse limit of the same complex of algebraic differential forms on each of the terms of the equations of S by I mod n. So this form a pro algebra, and you apply omega and you take the inverse limit and take the homology. Yeah, but this is not exactly how Grothendieck defined his homology. It is equivalent to this, but he defined it in terms of Grothendieck's topologies. So he put a topology associated to a scheme and an infinitesimal site, and this is defined as the homology of a certain sheaf on the infinitesimal site. This is what the H-inf spec A with coefficients in O is. And so in the particular case, when the schemes are affine as they are here, you can describe this as follows, and that's the next identity, this one that starts with an R that looks like the real numbers. This is not the real numbers, it means right-derived functors. And so let me explain all the terms there. There's a limit, it's an inverse limit, and the limit is taken over nil of com over A. So what do I mean by that? I mean all the nilpotent extensions of A by another commutative algebra, right? So you look at all of those, they form a category, and you can look at all functors from that category to abelian groups. Those will be my sheaves. So for example, you can, so if you have an extension, an nilpotent extension E of A, you can map it to E. And that functor is the functor O that appears there. Okay? So you have, again, the category of functors from nil com A to abelian groups. In that category, which is the category of sheaves, you have defined the functor to abelian groups, that is to take the inverse limit. Okay, so you have an abelian category, namely the functors from nil com over A to abelian groups. On that functor, you have the limit functor, and you take the derived functors of lim and apply them to the sheaf O. So if you do all that, then what you get is precisely this homology of the inverse limit of the differential forms. Okay, so that's what infinitesimal homology is. And well, why do I say this is the right theory? It's the right theory because Grothendieck proved that in this way, say, if you are over the complex numbers, you recover the homology. I mean, in the smooth case, the rank homology, and in general, you recover the Betti homology of the underlying space. And so, so this is the homology that you want. And in what sense does HP recover this? Well, it recovers this. I mean, it cannot be equal HP to H-inf, since HP is too periodic and H-inf is not. But Feger and Segan showed in a paper in Functional Analysis and Applications, 1985 too, that HP is the periodification of H-inf. So at each dimension n, you get HP n gives you the sum of all the infinitesimal homology groups of A of the same parity as n. Okay. So if we ask, what about characteristic P, where P is positive? Then, well, I mean, if we want to have a theory like HP, and HP takes the RAM theory from the commutative to the non-commutative setting, then we should start by asking first what the RAM theory is in characteristic P. The RAM theory. I mean, the bad RAM theory would be bad, at least for the kind of thing that I want. I want a homotopy invariant theory. And if you take the homology of the algebra of differential forms of, say, a polynomial ring over an algebra and of the algebra, then you get different things. So it's not homotopy invariant, so that's not the good theory. Right. So, but I forgot because I can, you know, with this control bar that Zoom has, I cannot see the title of my slide. Now I moved it. Okay. Yeah. Before going to characteristic P, I forgot to say something more about characteristic 0. That is that in the drive to prove excision for HP, Kunz and Quillen liked to put HP on formally on similar terms as H-inf. Okay, so what do I mean by this? Let me see here. There. Okay, so you have your associative algebra A. So it's no longer commutative, associative, could be commutative, but not necessarily. And then write it as a quotient of R mod J, where R is smooth, but in the non-commutative sense. which is what the Kunz and Quillen have called quasi-free. And then what you do, you complete R with respect to the J-adic topology and apply the X complex to that and take homology. And this amounts to the same as applying the X complex to the pro algebra of R mod all the powers of J and take the limit. So this is formally analog to the first construction I mentioned before of H-inf. There is also, one can also interpret this as some shift cohomology, but the shift cohomology is, has Hn with n bigger or equal than 0. It's 0 for negative n. Okay. But as similarly, if you take the non-commutative de Rham complex, it also starts at 0. So if you are willing to allow for that, so you look at only at n bigger or equal than 0, then you can also use the non-commutative de Rham of the completed algebra R, where for non-commutative de Rham, I mean in the sense that if the term was used, for example, in Karoubi's asterisk book, a whole volume dedicated to cyclic homology, K-theory and cyclic homology, which is to take the Rham complex, the non-commutative de Rham complex, and mod it out the universal differential graded algebra omega and mod it out by linear commutators. So if you do that, then you get a similar description as before in terms of shift cohomology, but now the shift, instead of being O, it's O modded out by the linear commutators. So we have a perfect analogy between H-inf and HP. Okay, so hence, if we look at characteristic P, then we should begin by looking at what the Rham theory is in characteristic P. And well, let's start with the commutative case. So as by what I said before, there's already a problem even for smooth algebras. And this is solved by lifting to characteristic 0. So you take a complete discrete valuation ring of characteristic 0. A discrete valuation ring is local and its maximal ideal is principal. So I write pi for a generator. And then you take this V so that when you mod out by pi, you get the field of characteristic P you were interested in. So you say if K is finite, you can take as V the bit vectors on K. And then the fraction field of V, which is a field of characteristic 0, since V is of characteristic 0, is obtained from V by just inverting pi. Okay, so now we want to define the de Rham theory of our smooth little k algebra A over little k. And then we choose a smooth lift of A. So we choose a smooth algebra over B, which reduces to A mod pi. This exists by a theorem of René-Elkick. And then we take the so-called Monsky-Basnitzer cohomology of A, which is obtained by taking the de Rham cohomology, in the sense of the commutative de Rham complex, of a certain completion of the algebra S tensor with F. So once you tensor with F, you are safe because you have a field that contains Q. So you're safe from certain problems that prevent you from having a homotopy invariant homology theory. by the fact that you can divide by natural numbers. And then the dagger that appears there, this dagger symbol, indicates the Monsky-Vashnitzher completion, which is a smaller completion than the p-adic completion, because the p-adic completion also has problems with homotopy invariance. So this is a smaller completion. I won't go into the details, but in the terms that I will use later, it's a bornological completion. So you take with S, it comes with the bornology, simply the bornology of all the finitely generated V submodules. And this bornology, as any other bornology, can be embedded in a so-called linear growth bornology. And the Monsky-Vashnitzher completion is the completion with respect to that bornology. Okay, so that's the smooth case. In a general case, you write A as a quotient of a smooth V algebra by an ideal I, and consider the tube of S around I. So this tube is the sum that I wrote there, which is the sum of the powers of the ideal, the I divided by pi, where divide means all the things of the form x over pi, with x in I, and airfoil products of that produce you pi to the minus r, okay? And this lives inside S tensor with the field F. Okay, and now you can apply this not just to I, but to all of I. And right, so that's what appears there. T of Si infinity, I use Kuhn-Squillen notation for the pro ideal of all the powers of I. Take the tube of S around that, dagger complete, tensor with V, with F, and take the dram cohomology. That's Berthelot's rigid cohomology. Again, this is not exactly how Berthelot defined his cohomology. It's I am using some results of Elmar Grosse-Kleene, because I mean this is also some theory that you can define, and that as Berthelot did, in terms of cohomology of shifts over a certain site. Okay, so if we are to define a version of HP in characteristic P, starting by our favorite Deram theory in the commutative case, which is this rigid cohomology, then we should start by adapting rigid cohomology to the non-commutative setting. And as we observed in the characteristic zero case, this was not as straightforward. I mean, it took Kuhn-Squillen several papers. And so here we have a previous work by Kuhn-Squillen done on what we have to do to prove excision, but then we have other technical issues. And well, so this adaptation took several papers and several authors and co-authors. As far as I understand, this project initiated in joint work of Joachim Kunz and Christopher Denninger, where they proposed a new way of looking at bit vectors, which are the V's, this DVR V that appeared in the previous slides. And so the lift of a field to characteristic zero, to a DVR of characteristic zero. And they wrote two papers, one in Münster General Math and another one in General Algebra. And then inspired by these ideas, so Kunz got that wanted to study this variants of the RAM in characteristic P and non-commutative generalizations. And he invited me to Münster in 2015, and we started thinking about these things. And then, well, Ralph Meyer joined us, and later Georg Tame too. And we wrote a couple of papers together in which what we did was a sort of analog of the Fagin-Segan theorem of writing H-rig, or rather its periodification, as HP of something, right? So this is in our two papers, one in Documenta and the other one in the Journal of Geometry and Physics. The latter was a volume dedicated to the CONFEST. And what we prove is the identity that is just put there. So on the left-hand side, we have the periodification of rigid homology of A, of our commutative algebra A. On the right-hand side, we have S. S was a smooth V algebra, which reduced mod I to A. And what we have on the right is the tube, the same tube that is used to define rigid homology, right? Okay, so this hints strongly that if we are to define HP of a non-commutative algebra, then we should, I mean, our non-commutative, the RAM theory of algebras over characteristic P, then what we should do is to write our algebra A as a quotient of a quasi-free algebra over V, take the tube, dagger complete, tensor with F, take HP, right? And this is, this needed, so that's the plan which we carried out. But first, we needed to develop this the Monsky-Wasnitzer dagger completion in a manner that was useful to us, because as I said, we think of the dagger completion as some bornological completion, but this is not how Monsky-Wasnitzer introduced it. They defined it as a certain subalgebra of the p-adic completion, and this, this bornological completion maps to the p-adic completion, but the map is not always injective. And so we needed to develop this quite ad hoc, and this was later more systematically done by Ralph Meyer and Devarshi Mukherjee in their joint paper on dagger algebras, which are torsion-free complete V algebras, which are dagger complete. So they are complete with respect to a linear growth bornology. And so we, with Ralph and Dev, we wrote a paper on analytic, what we call analytic cyclic homology for torsion-free bornologically complete algebras. So in all that I have said previously, you had an algebra for which you wanted to define, in a singular situation, say, or a singular algebra in characteristic 0, or an algebra, simply just an algebra on characteristic P, and then you lift this to some nice, smooth, or torsion-free situation, and then you apply the RAM theory to this nice situation, right? And so what we do in this paper is the non-commutative RAM theory for the nice ones, so the torsion-free bornologically complete ones, where nicety here means torsion-free. And then just this year, Ralph and Dev uploaded to their paper on analytic cyclic homology of algebras over the field of characteristic P, which has all the properties that, the nice properties that one would wish for. And one very nice property that it has is that if you have a Dagger algebra, so it's a chronologically complete algebra, torsion-free Dagger algebra, then which reduces mod pi to your algebra A, then the analytic cyclic homology of A is simply the analytic cyclic homology of this R in the sense of the previous paper. Okay. So as I said, this is in the archive. It has been uploaded 1 or 2 months ago, I think. Yeah, and so I highlighted in red and blue the paper on the torsion-free case, because that's what I'm going to talk about next. So I will concentrate on that. I will not say anything about the paper by Ralph and maybe Ralph will mention it in his talk. Okay, so analytic cyclic homology in the torsion case. So to complete torsion-free chronological algebra over B, we assign a pro-complex, HA of R, a pro-supercomplex of complete chronological vector spaces over the field F, which is the quotient field of our DVR V. Yeah, so this is obtained as I mentioned before. You write your algebra R as a quotient of a quasi-free algebra P by some ideal J, and then you take the tube of T around J and its powers and the Dagger complete, tensor with F, and take the X complex. Right. So this way you obtain a pro-Zucker complex, and then you get a complex whose you get a pro-complex that where the maps are not surjective. So the right thing to take is not the inverse limit, but the derived inverse limit, that is the homotopy inverse limit. You take the homology, and that's analytic cyclic of R. Well, and then what we prove is that this has all the desirable properties. This is analogous to Mayer's analytic cyclic homology, and Mayer's analytic cyclic homology is itself a generalization to chronological algebra or chronological algebras of Kahn's entire cyclic homology for Banach algebras. And it's analogous in the sense that, well, you take the complex for HP, right? Which in degree M has the product of all the bimodules of differential forms of the same parity as M. And inside there, you put a certain growth condition, and you consider only the strings, the sequences that satisfy that growth condition. Okay, so the growth conditions are different in the Archimedean case, considered by Mayer and Kohn, and in the non-Archimedean case, but the spirit is the same. Okay, so the theory that we get is C-mod 2C graded by definition, since the X complex is C-mod 2C graded. It is Dagger homotopy invariant. So what do I mean by this? Homotopy invariant, polynomial homotopy invariance means that the inclusion of an algebra into the polynomials is mapped by an isomorphism. Now, Dagger homotopy invariance means that the inclusion into the Dagger completion of the polynomials goes to an isomorphism. It is matricially stable in a sense, general complete sense that you can complete the M infinity in different ways, and the upper left-hand corner inclusion into any of these completions induces an isomorphism in analytic homology. And well, the theory is analytically nil invariant. So if you have an extension with nilpotent kernel, then you get an equivalence. But more generally, if the kernel is analytically nilpotent, then you also get an equivalence. And it satisfies excision. Yeah. So it's good properties that you may want to have, and as it happens with many of the theorems about K-theory, say, then you can prove many things just using that HA has these properties without anything else but these properties. So, for example, to give you a concrete example of some non-commutative algebras for which using this we can compute HA are the dagger complete Leavitt path algebras. So say you have a directed graph E with a set E1 of edges and a set E0 of vertices, and range and source maps are an S. And we will assume that it has finitely many vertices, and consider the regular vertices, which are the vertices that emit a non-zero finite number of edges. So I write reg E for that. And I consider the Leavitt path algebra over V, which, if you're not familiar with it, but have heard of the Kunz-Krieger algebra of E, well, it's the same, but without the completion, right? So it's an algebra generated with a star algebra with generators and relations generated by the vertices and the vertices and the edges, without the completion. If you take the C-star algebra completion of that, the universal C-star algebra, you get the Kunz-Krieger algebra. Yeah, and the Leavitt path algebra can be defined over any ring, for example, over V. And then you can dagger complete it. And this is what I mean by the dagger complete Leavitt path algebra. Now, to express the calculation of HA, I need some notation. So I consider the matrix M, which depends on E, that has as many rows as vertices E has, and as many columns as regular vertices it has. Then the BW entry of M is Kroneker's delta BW minus the number of edges that go out of W and end up in V. Okay, so the theorem is that the calculation is that the analytic homology of the dagger completed Leavitt path algebra is given by the kernel and the co-kernel of this matrix tensor with F. So this follows purely from these properties that I put in previous slide, these properties of HA. And let me point out that if you look at the Kunz-Krieger algebra of E and take its Banach algebra K theory, then you get the same thing except for the F. So here's my remark, is that if you take the K-theory of the sister algebra of B, the Kunz-Krieger sister algebra of B, take its K-theory tensor with F, then you get exactly the same. Okay, so it's a nice thing that what you should get. Okay, but you may have noticed that I started with rigid cohomology. I emphasized the Fagin-Segan theorem, blah, blah, but so far I haven't said anything about the agreement between this analytic theory defined for all commutative, for all associative algebras, and the rigid cohomology that is defined for the commutative algebras. So concerning that, we have the following result. So say if you have a smooth algebra of dimension 1 over our little field K. So A is commutative and smooth of dimension 1. So that's a curve, right? And here the dimension 1, well, geometrically it means that it represents a curve, and algebraically it means that the rank, so first of all, that the modulo of Keller differentials, so one Keller differential forms, is projective and of rank 1. And now we take a smooth lift of this algebra to V, in the sense that S mod pi gives you back A. That is also of relative dimension 1, meaning that the module of Keller differential of S over V is projective of rank 1. Then the dagger, the analytic cyclic homology of the dagger completion of S is the rigid cohomology of A. Okay. So here there is no periodification because there are only two rigid cohomology groups because the dimension of A is 1, right? 0 and 1. In general, you would expect to have this without any restriction on the dimension. And it should be true that HA of S dagger is the periodification of rigid cohomology of A. So why do we need this dimension 1? Well, you may recall that the smooth commutative algebras are usually not smooth in the non-commutative sense. They are not quasi-free, except when the dimension is 1. So when the dimension is 1, so my S, because it's smooth of relative dimension 1, it is quasi-free. And this is the key for our proof of this. What happens in the general case when you have arbitrary finite dimension? Well, I mean, if you recall, so there is this paper of Masoud Khalkhali, where he considers the situation of Banach algebras that have finite homological dimension, right? And so for such algebras, he proves that analytic or entire cyclic homology is the same as periodic. And and so here we want to do something similar because by the paper that we have with Joachim Kunz, Ralph, and Georg Tame, we know that the periodic rigid cohomology is HP of the algebra, right? And so what we want is that HA is HP. And what do we know? We know that S is of finite homological dimension. So we want to use this trick of Masoud to repeat the same proof. But then I mean, the idea, Masoud's idea, is to use, I mean, the fact that you have finite homological dimension n gives you a connection on the module of n differential forms, n non-commutative differential forms. And using this connection and using con big B operator and iterating compositions of the nabla being the connection and the B, you get a contracting homotopy, you get a homotopy equivalence between the periodic cyclic complex and the analytic cyclic complex. But if you do this, in our case, you need to prove that the resulting map is bounded. And there are some factorials there that do not allow us to prove this. So it might be, it looks like, since the big B operator involves certain permutations, that and you apply these names, that this will add some factorials that would allow us to prove that the map is bounded, but we haven't been able to do this. This is very combinatorially involved, and so that's why we do not have the result in general. Okay, so that is all I wanted to say. Thank you very much.
Thank you. You were exactly on time. So now we have time for